Hello, everyone. This is Mr. Minnick. Mr. Minnick's my name. Math is my game. Some people call me the Math Overlord. I will be uploading this video to YouTube for your viewing pleasure. This is called the number system. You might ask yourself, why do I care? The same reason you care about keep piling cards on 5 giant stacks. What are you talking about? You don't make any sense. You're just going off on random tangents. Keep piling cards on 5 giant stacks. Like that's ever going to help me in a biology class. Each of us is a human, right? In theory, we're humans. Some of us may be from a different planet, but never mind, that's another story. So anyway, human beings have a certain classification. Human beings are called Homo sapiens. Homo sapiens, right? True? Okay. And human beings, believe it or not, whether you want to think so or not, human beings are actually animals. Right? You don't think so, but we are. And then I don't know where else this one fits in. Maybe somebody can help me. But we do have a backbone, at least some of us. Vertebrates. We are vertebrates, right? I don't know where this vertebrates one belongs, so I don't want to put it in the wrong place. Maybe in a second comes. Does anybody see where I'm going with this? What is it? It's the taxonomy, isn't it? So we are members of the animal kingdom, all right? And then you go to phylum, and then you go to class, and then you go to order, and then you go to family, and then you go to genus, and then finally species. Keep piling cards on 5 giant stacks. There's actually one for the metric system as well, but I'm not going to say that one today. I can't say that one today. So anyway, there is a hierarchy to classification of people and things, right? In animals and plants and whatnot. Similarly, we have a classification of numbers, and it goes like this. When you first learned how to count, I love hearing little children count. This is great. I'm going to turn my microphone up live for this. It's so entertaining when little children count, because they hold up their finger and they look at it and they stare at it for a minute, and their parents ask them, okay, go ahead and count to 10 for me. And they stare at their finger and say, 1. And they're proud of themselves because they can count, right? So they look at their fingers and their mouth starts quivering and they say, 2. And then they hold up 3 fingers and they look at it and 3. And then they hold up 4 fingers and they say, 5, 4. And then they hold up all 5 and they 5. And then they hold up the 1 on the other hand. And it's always the index. When they count to 6, it's always the index. It's weird the way people count. 6, 7, 8, 9, 10, 11, 12, 14, 17, 28, 85, 97. 1, 2, 3, and so on. Those numbers have 2 names. Why 2? Because that's what mathematicians said. Don't ask me why other than that. They have 2 names. In math, everything makes sense. We're going to get to 1, and you're going to say, well, that doesn't make any sense at all. Well, it will. Trust me. So those are what we use to count. Captain Obvious. What would you call those numbers? Counting numbers, sure. They're called counting numbers. If those numbers were food, they would be called organic. If those numbers were food, they would be called organic. Because of that, another name for these numbers is natural numbers. Natural. So I'm going to keep coming back to these boxes, and this box is going to get smaller and smaller, and there's going to be more and more of them. So on this first page, what I'd like to do is talk about these counting numbers. Counting numbers. There is a letter that we use to represent the counting numbers, to represent the natural numbers, and it's a funny looking N like this. Okay? On the homework that you're going to have over this, there's going to be a worksheet, and it's going to say what all number systems does each of these numbers belong to. And we're going to be listing a whole bunch of them. You probably already know what about 7 of them are right now. So anyways, when we talk about the set of natural numbers, we do use braces. Remember set notation? We do use braces. Some of you call those francs. That's fine. Braces to enclose these. In every textbook you'll ever see, they're written 1, 2, 3, and then there's 3 dots. If you don't know what those 3 dots are called, shame on your English teachers. Those are called the dots of ellipsis. It means it continues for a long time, forever. So those 3 dots, some people want to put 5, some people want to put 2. It's just 3. Those 3 dots mean it keeps going. It keeps going. Okay. We'll come back and add something to this in a minute, but those are the natural or counting numbers. Counting or natural numbers. Okay. Does it make sense that we used a capital N to describe the natural numbers? Okay, good. Well, so after you learn to count, then all of a sudden, your parents, grandparents, whoever, they say, you know, you're responsible now. You can count to 100. So we're going to give you an allowance. And then you go to the store and you spend it all. When you spend it all, then you have $0 left. So now we introduce the number 0 and 1 and 2 and so on. And this set of numbers has one name. There is a reason that I picked the color that I picked to write this in. I love to drink milk. I like milkshakes also. But anyways, when you're drinking milk, you should drink this kind of milk because it's the best. Yeah, this is whole milk. And these are the whole numbers. Okay? Those are the whole numbers. So, the whole numbers. The whole numbers. What do you reckon we use to describe the whole numbers? What letter? Yeah, we use a W. It's a big fancy W. I don't know how to make W's real fancy. So pardon my lack of fancy W here. I don't know. So you like that? So here's a W, here's a 0, and a 1, and a 2, and a 3. Well, we don't even need the 3. And a dot, dot, dot. So that, when we use the braces, that means that's the set. That's the set of whole numbers. I don't understand it. When people say white, some people, when they say the word white, they say white, like they put an H before it, even though the H is after it. How come people don't do that with whole? They don't say whole. I don't get it. The English language is so weird. Anyway, enough of that. Ain't nobody got time for that. We got to talk about these number systems, and we got a lot more to get to. So back to growing up, back to drawing random red lines on the paper because your smartboard doesn't like you. Okay, that's the second one. One more, and I think I'll go to the, there we go. That's better. So I said that this box would keep getting smaller and smaller, so it's going to get smaller because now, when you get a little bit older, you ask your sister, could I please borrow $200 to pay a speeding ticket so mom and dad don't find out? That's when you start borrowing money. Negative $200, negative 1, 0, 1, 2. And interestingly, what happens too is when you take home this homework, and your whoever's helping you with the homework, if it's your parents, grandparents, brothers, sisters, whoever, chances are they're going to look at the words on your paper and they're going to roll their eyes in the back of their head and say, I don't get this. If you need help with this, you're going to have to go ask your uncle or your aunt or go get a tutor. Oh no, we're going to lose the house because we got to hire a tutor because you're in this stupid math class that's got all this crazy stuff that's going on and nobody understands that. They didn't have that back in my day. What are these things called? Somebody said it. Say it loud, say it proud. It starts with an I. They're called integers, not to be confused with an Acura Integra. They're called integers. The word is intimidating to look at. It really is scary. People see that and they say, well, that's foreign. Well, it's not a word you use every day. It's not foreign, it's English. It just means it's another number set. It's not that bad. So these are called integers. By definition, they're the whole numbers and their opposites. That's what the definition of this is. It's the whole numbers and the whole numbers is opposites. By definition, it's the whole numbers and their opposites. So let me go back. I said I'd add some to this whole numbers. The whole numbers, then we can think of these as the natural numbers. We can think of these as the natural numbers and 0. We could think of the whole numbers as the natural numbers and 0. Similarly, we could think of the counting numbers as simply the positive whole numbers. As positive, well, actually positive integers, I guess. So counting numbers are really just positive integers. Whole numbers are natural numbers and 0. Integers are whole numbers and their opposites. How's everybody doing so far, okay? But we need to talk about transmissions for a minute. I'm kind of disappointed. Back in the day, you used to be able to go to the car dealership and buy a car that had a transmission that was a manual shift. And you didn't have to pay for it. That's how they came. And if you wanted automatic, you had to pay an extra couple $1,000s for automatic. Nowadays, everything's automatic, and you can't even get a stick shift. Some cars you can get a stick shift, and you actually have to pay for it if you do. Anyway, the point is, back in the day, they didn't have park. A transmission didn't have park. A typical 5-speed would have a 1 here, and a 2 here, and a 3 here, and a 4 here, and a 5 here, and usually reverses over here. A typical 4-speed would be a 1, and a 2, and a 3, and a 4. And 4 speeds are weird because they put reverse wherever they want to. Some of them put reverse way up here. Some of them say, no, we don't want reverse there. Some of them say, reverse belongs down here. So it'll hit your knee every time you got to put it in reverse. And some say, no, if you have a passenger, let's hit them in the groin every time you go to put it in reverse. So let's put reverse over here. And some say, no, we like you to bust your knuckles. So let's put reverse all the way up here up against the dash. So when you put it in reverse, you're going to bang your hand on the dash. Okay? Because nobody needs to back up. Well, anyway, so when we had these kind of transmissions, there was like a slider here, and that slider indicated a gear. What's that gear called? Yeah, it's called neutral. The whole point of that, the whole point of neutral is that 0 is neutral. What I mean by that is 0 is not positive, 0 is not negative, okay? 0 is not positive, 0 is not negative, 0 is neutral. Sorry about the lesson on transmissions, but it was kind of fun to talk about hitting your fingers on the dash, because if you've ever driven a stick, you know what I'm talking about. My worst reverse, I have 2 really bad reverse experiences. Reverse experience number 1, my boss told me when I was a mechanic, if you could drive this bug, if you could back it out of the shop, you can take it for a spin and go romp on it. And it was a turbo diesel bug, and I really wanted to drive it. I couldn't get the thing in reverse. I had no idea. You have to actually push down on the shifter to get them in reverse. It was a stick shift. And then my neighbors, I'm 6'2", 200 and some pounds. My neighbor, the guy was 6'3", 350, and his wife or girlfriend was like 5'8", about 250, and we were all in my S10 in the front. We had to go somewhere, and he sat in the middle, and it was pretty bad. I didn't shift into first. I didn't shift into second or fourth, but I did have to back up. That was really awkward. But I just shifted from first to third to fifth. But anyway, enough about transmissions. We got work to do here. So this integer set, there's no surprise what the integer set looks like. We've got these three dots. What do those three dots mean? It means it goes on and it's called an ellipse or ellipsis. So anyways, we got a -2 and a -1 and a 0 and a 1 and a 2 and a dot, dot, dot. Now, I told you this is where your parents say, we need to hire you a tutor. This is one exception in mathematics where things don't make sense. Okay? It's a Z that we use. Do you remember that? It's a weird Z. Why do they use Z? I honestly don't know. If somebody can find out why it's a Z here, please tell me. Maybe because 0 is a neutral number and it's like the divide. Could be. Could be. Like everything's partitioned around 0. That's the most sensible thing I've heard about that so far. All right. Well, we're moving along. We still got more of these. I said this box would keep getting smaller and smaller because then in 7th grade, your 7th grade teacher said, go to Rite Aid and buy a TI-30X2S. And life will be grand because if you go down 3 buttons and in 2 buttons, there's an ABC button and it's going to be your friend. And you'll never need to worry about these numbers ever again until varsity math. And then it's Mr. Minnick's problem. Well, what I'm talking about here is these kind of numbers. 0.8, 7/16. There's a little bit of latency in the smart board. It's kind of fun. Anybody know what these numbers here are called? Yeah, they're rational numbers. Nice, good. They are called rational numbers. Okay, let me get my box going here. Let me get the color, the right color here. Fill it in. There we go. We'll make it gray. So these are called rational numbers. Rational. Good. Everybody doing all right so far today? If you're watching this back, I hope that this is informative and you learned something other than the fact that I had neighbors who I had an awkward moment with them in my S10. So rational numbers. Rational numbers. Some of you are going to see that the letter we use for rational numbers, and you're going to say, that doesn't make any sense, but it will. Just bear with me. By definition, this is any number. Any number. I abbreviate number with an NO dot. That's like a universal abbreviation for number. They used to use the pound sign, but now you don't call it the pound sign or the number sign. Now you call it the hashtag, which I don't understand. But anyway, ain't nobody got time for that. Hashtag LOL. Any number that can be written as check it out, in the definition of rational numbers, we have the word ratio. Oh, that's why we call it that. Yeah, you're right. Any number that can be written as the ratio of 2 integers. I'd like to introduce you to existential quantification. Huh? What? Come again? Existential quantification. Existential quantification. It sounds like a really big, complicated thing. It looks complicated. It looks scary. There's all kind of new symbols you're going to see. You're going to say, are we in Russia? Because those look like Russian letters. So existential quantification. In math, there are certain symbols that we use that really are symbols. If you don't believe me, Google existential quantification. There's one word, there's one symbol that means for all. It also means for each. It also means for every. And it's a weird letter. Don't ask me why it is what it is, but it's an upside down A, like that. That's what it is. That's what it is. Similarly, there is an existential quantifier for something, meaning that is contained in the following set. Mathematicians are really quite bright, because who wants to write all that? That is contained in the following set. Instead of having to write all that, mathematicians said, here we go. Just make that simple. Just make that simple. It looks kind of like a, what's that thing that you throw? I can't remember the name of it. It'll come back to me. Oh, yeah, that. Okay. So there's existential quantification. So hopefully this next thing's going to make sense. Okay. So here we go. When we write the set of integers or the set of rational numbers, here's how we write it. We write it this way. We write it as A divided by B, comma, upside down A, which means for all, A and B contained in the set of. Did we get to, we talked about integers already, right? What represented integers? Integers was a Z. So what that's saying is, so a rational number is any number that can be written as the ratio of A to B, where A and B are integers. So if you need a translation, this is saying for all integers A and B. It's just saying A and B are any integer, it's A divided by B. And there's one other stipulation to this. There is one other stipulation to this. B is not allowed to equal 0 as well. And that's another story. Hopefully we'll have time to talk about that in this lesson, but not right now. So what's a sensible letter for rationals? R, but R is used for something else. They use a Q, and it never used to make sense to me, but one day, just like the boomerang came back to me, one day it struck me why this is what it is. Let's think about this for a minute. When we talk about a ratio, let me get my magic marker going here. Whenever we talk about a ratio is essentially a fraction, right? Now, to me, it's kind of sensible that rational kind of almost rhymes with fraction. Rational, fraction. Ratio, though, is a fraction, true? What mathematical operation is involved in fractions? Division, thank you. And when you divide, what's the name of the answer? The quotient. Oh, it all makes sense now. Now I get where the Q comes from. Everybody okay with that? Okay, good. Well, we got a long way to go. So far, what I want you to realize, and this might be difficult to realize, especially when I'm drawing black lines on the board instead of regrouping these to move them down a little. Let's go all the way back to the beginning. So humans are animals, and humans are Homo sapiens. You remember how everything belonged to something else? I'm not going to quiz you over this like your geometry teacher quizzed you, like your geometry class quizzed you about is a rectangle a square and is a square a rectangle. Remember those questions? Those were horrific. Anyway, I do want you to be aware that every single counting number in the whole world is a rational number. And in tonight's exercises, you're going to be doing this. Every single whole number is an integer. Every single integer is a rational number. Is every whole number a counting number? Are all whole numbers counting numbers? No. Are all rational numbers counting numbers? Are all integers counting numbers? No, but a lot of them are. Here's one that'll blow your mind. Actually, there are an infinite number of integers in the set of counting numbers. Right? Anyway, does everybody get how everything fits together so far? I hope it makes sense. So far things have been contained within other things. Things have been called subsets. In advanced math classes, they study these concepts of sets and subsets and groups. Well, I'm going to use a phrase, and don't take this phrase the wrong way, but this phrase, this word, actually, it's not a phrase, means that this is separate from that. or disjoint. Okay, I'm not talking about this place or this marijuana cigarette. I'm talking about separate from. Okay, it's separate from. When I say the word disjoint, that's what I mean. It's separate from. Okay, so separate from the rationals. I love the English language sometimes. Math makes more sense, but if something's not rational, we add a two-letter prefix to the front. Yeah, and it's irrational. It sounds like the word ear, but it's irrational. Now, mathematicians are real funny. You know what happens when they run out of ways to describe stuff? They make up words. Well, sometimes, and then they use really El Cheapo ways of describing things. So with this irrational thing, we're going to talk about this, and then we'll go back and look at the existential quantifiers again in a second, because I might even show you another one of those. Irrationals. Let me write up a thing or two about irrationals real quick here. Irrationals. Irrational numbers. Irrational numbers. Any number that cannot be written as the ratio of two integers. Remember, rational numbers could be written as the ratio of two integers. Irrational numbers can't. So mathematicians say, you know what rational numbers are? Well, irrational numbers aren't those. I think that's funny. So it's almost impossible to put things in a set, to put particular things in a set. I can give you some examples. I can show you what letter we use. What letter do you suppose we use for irrationals? We use an I. We use just a capital fancy I. Okay? So that's an I. That's not a 2. It's an I. Some examples. Some examples would be the square root of 5. Would be not 3.14, but where it actually comes from, the ratio of a circle's circumference to its diameter, the number pi. A mathematician by the name of Leonard Euler came up with a very fascinating number we'll study in great lengths in chapter 7. There is a number called E. Now, math books go on to say some stuff about irrational numbers that's noteworthy. So let's do this. Irrational numbers are non-repeating, non-terminating decimals. That is, they go on forever, they don't repeat. Like pi, some people memorize pi to a bunch of decimal places. At one point in time, I knew it out to 70 decimal places, but ain't nobody got time for that. 1/3, let's think about 1/3. 1/3 is an integer over an integer. 0.3333 does repeat, so it's not. It's a non-repeating, non-terminating. So let's go back to rationals. Let's go back to rationals for a second, because rationals, what we need to say are 2 bullet points here. Rationals are repeating decimals. Repeating decimals. Such as 0.111111 and so on. That actually is rational. I don't know if you know what fraction that is, but it actually is. Also, it's a terminating decimal. It's a terminating decimal. So 0.875. Okay. How's everybody doing so far? Good. So I said we'd go back to existential quantifiers. We had a request about something about that. So one more existential quantifier while that's up that I'm going to write in blue is this one. And this one actually means such that. It's kind of a weird symbol, but that one actually means such that. Wow. Existential quantifiers. That is contained in the following set for all such that. Everybody doing okay? Okay, so we gotta tie all this together. Because in the taxonomy here, with taxonomy, we had this to tie everything together, right? Well, we need to see how this all fits together. So, mathematicians said, everything's got to belong to something else because that's just how sets are. With a set, everything's got to belong to something else. So, let's put one blanket name for all this. That'll cover all that in a bag of chips. And these are called not the number system, the real numbers. These are called the real numbers. It reminds me of that Lone Max commercial. That drives me bonkers. Your money, your real money. Ha! I hate that commercial. Anybody ever hear it? The Lone Max one? Drives me absolutely bonkers. So this is life as you know it with respect to number systems. Your first grade teacher, your second grade teacher, your third grade teacher, fourth, fifth, sixth, seventh, eighth, ninth, up to ninth, maybe even 10th grade, that's all you knew. Some of you might be in 10th grade this year. Some of you watching this video might be younger than that. But anyway, those are the only numbers that people know until electricity came along. Thanks, Edison. Thanks, Tesla. Thanks, aliens, for reverse engineering. I didn't say that. So let's go to the real numbers here and just show the symbol that we use here. Real numbers. Real numbers. It consists of the rationals and the irrationals. So that's what the real number system is. And so basically what we have is a capital R to represent the reals. Okay. And let me just show you some existential quantification here. It's the union of, how do we represent the rational numbers? How do we represent rationals? With a Q. It's the union of the rationals, and how did we represent the irrationals? With an I. So it's the union of the rationals and the irrationals. This upside down U, when you get to trig, Mr. Camuso is going to show you this. It's called the union of the set of rationals and irrationals. So if you put those together, that's what the reals are. It kind of looks like some African word, doesn't it? Rokoi. Yeah. It's probably the name of a prince somewhere. What's your leader's name? Rokoi. Okay. I shouldn't. I don't know. Anyway. So we got all that, and I said, well, Tesla came along and ruined everything. Edison came along and ruined everything. Aliens came along and built the Mayan temples. And the Egyptian pyramids. Oh, no, I better stop with that. Disjoint from that, disjoint from the reals are some other ones. When you were 5 years old, you had this kind of friend. You had an imaginary friend. And when you try to solve quadratic equations, your ninth grade teacher said you can't solve ones where you take the square root of -2. And I'm here to tell you you can, because we have imaginary numbers. Thanks, Mr. Minnick. You're welcome. Don't thank me. Thank Edison. Thank Tesla. 7 minus 3i. What the heck does that have to do with anything? Well, if you ever take electrical engineering, you'll know. In Chapter 4, Section 8, you'll know. So Don't ask me how we talk about imaginary numbers on tonight's worksheet. Don't worry about imaginary numbers. The final component of this is this. We are going to encompass all of these with one final grouping here, and I hope I could pick a color that doesn't screw up the contrast. Pink. I'll try pink, see what happens. That worked okay. So it's not as complicated as somebody might make it. When we combine the reals with the imaginaries, it sounds complicated, but it's not as complicated as you might think. Anybody know what this is called? What these are called? Collectively, all these are called complex. All these are called complex. All those are called complex numbers. So we had pi, we had e in here. Okay. So what kind of number is pi? Well, pi is irrational. Pi is also real. Pi is also complex. What kind of number is 7? Well, 7 is a counting number. 7 is a whole number. 7 is an integer. 7 is rational. 7 is not irrational. 7 is real. 7 is complex. That's the kind of thing we're going to be doing tonight. You ready for an example? Here we go. Here we go. Here we go. Example numero uno. Name all the sets to which each number belongs. So number A, we'll start with 1. They say that 1 is the loneliest number. Yeah, it's a song. 1 is the loneliest number that you'll... Yeah, it's a good song. So let's name some of the sets that 1 belongs to. Somebody throw one out. What do we got? I heard natural, good. You can abbreviate, so 1 is natural. What else is 1? 1, I heard a whole. 1 is also whole. I heard counting. Counting and natural are the same thing. I heard integer, good. 1 is an integer. What else? 1 is rational, you're right. And let's talk about that for a minute. You might think, wait a minute, 1's not a fraction. Oh, but it can be written as a fraction. You can write 1 as 1 over 1. You can write 1 as 8 over 8. You can write 1 as 11d2 over 11d2. Right? True? It can be written as the ratio of 2 integers. We're missing 1. Actually 2. Reals, good. And also the one that encompasses everything that we're going to study this year. Complex, good. Complex. All right, let's move on. For the second number, let's go to psi. No, it's not psi, it's phi. That's the number phi, P-H-I, phi. Otherwise known, and it's weird because it's called a golden ratio and it's kind of misleading. Anybody ever see this number? It's a really fascinating number. It's called the golden ratio. It's actually given by, I wish I knew the right formula. There's some quadratic equation. It's like rad something plus or minus rad something else. Anybody know what kind of number this is? Yeah. It's approximately 1.618. Yeah, so it's 1.618 something, and it keeps on going on, and it doesn't repeat and it doesn't terminate. So this is irrational. So this is irrational, and it's also I shouldn't have put it there. The smart board kind of it's like 1.6 something or other. Yeah. So it's irrational. What else is it? It's not imaginary. It's real. And there's one that we're missing that encompasses everything. It's also complex. It's also complex. Good. Now, what about the square root of 324? Now, wait a minute. The square root of 2 we said was irrational, but what about the square root of 324? In a couple of weeks, I'm going to ask you to memorize the first 20 perfect squares. 1, 4, 9, 16, 25, 36, 49, 64. That's 8. 81, 100, 121, 144, 169, 196. That's 14. 15 is 225, 256, 289, 324, 324. 324 actually is 18. So what's the square root of 324 going to be? What kind of number? It's going to be natural, good. It's going to be counting and natural, the same thing. It's whole. It's an integer. It's rational. It's real. And complex. Do we get the idea of this, the hang of this? Any questions, comments, concerns about the hierarchy of the number system? Can you write the box down? Yeah. So I'm going to put this back up. It's been real. It's been fun. I hope this has been informative and educational. Again, this will be on my YouTube channel for all the world to see. Any shout outs? Dane Burrows gets a shout out. The future Mr. Minute gets a shout out. GHS gets a shout out. And that's probably it. Have a great day. Bye.